In today's session, let's see the hypothesis testing hands-on. So I have already covered the hypothesis testing using Z-test, and also we have seen concept called our ANOVA. Now let's do the hypothesis testing, how it is done on t-test. So let me show you the t-table first. So this is the t-table. So you need to understand that the t-test is only limited in some cases when your data, your records are, I mean, if you have very less number of records, or I can say if your sample size is less than 30, then only you can go with t-test. Otherwise, if it is greater, the sample size is greater, then you can go with z-test. So I want to say you, if you see the sample size over here for t and for z over here, it for 30 you can see it's almost till one decimal. It's almost same. Like it's t-test, the value is t value comes out to 0.683, whereas z value comes out to be 0.674, and it comes out to be 0.85 and 0.842. So we can say that. So when the sample size is greater than 30, then value becomes z value. Okay, so you can go with z test, z value when the sample size is greater than 30. And also, these are the values. You can see the cumulative probability in the upper. So for one tail, 0.5, 0.25. For two tail, it's double that size. So let's see some of the hands-on that is performed on hypothesis testing using t-test. Okay. So just remember that in t-test, when sample size is less than or equal to 30, then you will go with t-test. If sample size is greater, then only you will go with z-test. And if your samples, if you are not confident about your data, okay, if you are not confident about your data, then also we will go with the t-test. So let's see them hands-on. So, so this is the hypothesis testing hands-on. So let's start with one sample t-test. So t-test one sample. So one sample t-test, the one sample t-test determines whether the sample mean is statistically different from a non or hypothesis population. Here, the known or hypothesis population mean we are taking a static value, okay? So we are just considering one sample and then we are considering one hypothesis mean, hypothesized population mean, that is a static value. The one sample t-test is a parametric test. Example, you have 10 ages and you are checking whether average age is 30 or not. So let's see this example. First thing is that let's take ages variable where we will have a list of values over there. Let's have 20, 25, 30, 31, 54. So we have a list of values where we have an ages variable which contains ages of people. So now let's, for performing t-test, let's first import t-test one sample. Okay, since we are taking only one sample, so let's import t-test one sample. So we are actually importing from scipy.stats, from scipy.stats import t-test one sam, t-test underscore one sam. So we have imported one sample t-test from scientific Python stats. So now let's import numpy. NumPy is used for numerical operations on array. So let's print ages first. What happened? You just write. Sorry, actually this is t-test one sam. Okay, you have to import t-test one sam. That is for one sample t-test. Okay. Now let's find out the mean of this overall age. Overall age is given. This is 56. Sorry. Okay. Let's see the mean of the ages. So ages mean print np dot mean of ages. Okay. So the average age is 33.77. So now let's find out the t value for using t-test one sample. So there is a function called so this is the function t-test sam. So this actually returns two values. So let's that is t value and p value. P value is the probability value. So always when you are doing hypothesis testing using Python, always take p-value because it's easy to find out p-value and computationally it's only one step. Whereas if you go with the t-value, you have to go with the t calculated and also you have to find the t tabular. From t tabular and t calculated, you have to find and then you have to compare that values to see whether your null or alternate hypothesis is true. So instead you go with p-value, it's simple. Okay. So now let's pass t comma p-val is equal to t comma p-val. So t-test sam one sam returns two values that is t and p-value. So we have t-test one sam of. So let's see the parameters that are present over here. So let me first. So now let's take this. Happen t-test one sample, right? T-test one sample. Okay, it comes out to one sample. So in t-test on SAMP, we have following parameters. So we have for this is let's see the question first. So the one sample t-test. So we have 10 ages and you're checking whether average age is 30 or not. So this is alternate hypothesis. Okay, average age is 30 or not. That is our mean is equal mean average is not equal to 30 is your alternate hypothesis. And whereas null hypothesis says your mean value is 30. Okay. You have 10 ages and you are checking. So we have taken more than 10 ages over here. So we are checking whether average age is 30 or not. So here you have to pass the array first. That is A is an array over here. So let me show you. So A is an array. So you have to pass an array and also you have to pass the population mean. So population mean is the static value that we are passing here, which is 30. So and also alternates it two sides. So since our the alternate hypothesis says mean is not equal to 30, whereas our null hypothesis says mean is equal to 30. So mean equal to 30 means alternate becomes mean less than or greater than 30. Okay. So this is a two-sided test. Okay. So and also now you pass here A and that is array and population mean that is this ages list and also you will pass the population mean that is a static value of 30. So you don't have to pass the alternative because this is a two-sided uh, test. Okay, so I mean this is one-sided, two-sided tail. So now let's pass ages first, ages comma 30. So we have passed ages. Let's print p-value. So p-value comes out to be 0.0827. So now let's print p-value as well. So t-value comes out to be 1.75. So while doing has hypothesis testing on Python, I would suggest you to go with the p-value and compare. So let's see our alpha is 0.05 since alpha is 5%. Usually alpha by default we take 5% if it's not mentioned in the question. So we are taking alpha as 0.05 now. We are comparing it with 0.05. If p-val less than 0.05 and print. What will you print? Print null hypothesis. That is, we are rejecting the null hypothesis. And else print we are failing to reject null hypothesis. Okay. So now let's print this. So since p-value is less than 0.005, we are failing to reject null hypothesis because p-value is 0.08. So since it's a two-sided test, you don't have to worry. This SciPy function will take care. That is, t sample will take care because we have passed. It's a two-sided. Okay. It's a two-sided tail. So you don't have to worry about here. What is the alpha value? You don't have to pass 0.25 over here. Have to pass 0.05. Internally, the function will be taken care of. That is even the SciPy scientific Python, the SciPy library will take care of that internally. So you don't have to worry what is if it is a one tail or two tail test, because we have already passed here by default. It's for two tailed, okay, two-sided test, okay. So as I said, we are rejecting null hypothesis because the average age is greater than or less than equal to 30 is or an alternate hypothesis, but our null hypothesis was average is equal to 30. So since our p-value probability value comes around 0.05 less than 0.05, that is, if p-value is less than 0.05, this is false. Since our 0.0 p-value is greater than 0.05, we can see that our p-value lies in the acceptance region. Okay, so let's see that over here. So let's take this as example. So we have given the alpha as for 0.005. So this comes out to be 0.25, okay, and this also comes out to be 0.25. But we have given it is a two-tailed test. So internally Python will take care of that. Scientific Python library will take care of. So since we have we have passed if p-value is less than 0.05. That is, if p-value was over here, if this is 0.05 the total, if p-value was over here, then we would have actually accepted null hypothesis. But it has crossed the significance level. So we are actually rejecting null, we are failing to reject null hypothesis because our p-value actually lies in this region. Okay. So we are failing to reject null hypothesis because the p-value lies in the acceptance region. Okay. So if p-value had been lesser, then we would have rejected null hypothesis. But p-value is greater than 0.05. So we are accepting null hypothesis, or we can say we are failing to reject null hypothesis. So now let's see so this is the what we have done. Compare p-values. That is what we have done over here. P-value for my rejection region is 0.05. That is significance level is 5%. So 0.05 becomes a p-value for rejection region. So compare statistics, critical value, and I will compare the t-cal with that. Okay, so what I wanted to say is that when you are going with t, right, if you are instead going with p instead of p value, then you will be calculating the critical value, and then you will actually compare that with t calculated. So if critical value of t is less than t calculated, then we are actually accepting the null hypothesis. If the critical value is greater than calculated, then we are rejecting null hypothesis. Now let's do the two sample t-test. So we have seen one sample t-test previously. Now let's see the two sample t-test. So in sample t-test, what happens is that previously we had taken in one sample t-test, we had taken one sample and we had compared that one sample with the static value, that is 30. Now in two sample t-test, we are actually taking the two independent samples, that is two sample t-test. The independent sample t-test or two sample t-test compares the mean of two independent groups. Understand? The mean of two independent groups are compared in order to determine whether there is a statistical evidence that is associated, but the associated population means are significantly different. The independent sample t-test is a parametric test. The test is also known as independent t-test. Okay, so the two sample t-test is also known as independent test. Example, is there any association between week 1 and week 2? So let me first import the independent t-test, which is the two sample t-test from scipy.stats library. Scipy from scipy.stats import. So now we are actually importing two for two tests, two sample tests, that is independent test, t test underscore int. This is actually, this function is used for two sample t test. IND represent independent t test. So let me once again read the question. So the independent sample t test, uh, the independent sample t-test or two sample t-test compares the mean of two different independent groups. Okay. So mean of two independent two independent different groups, right? So first, let me import NumPy as NP. So let's take a week one. Week one, this is the week one week one variable. So week one variable, let's actually take one random distribution or random uniform distribution, np.random.uniform of, let's give the low value to be 10.20 and high value to be 25.3. And in that uniform sample, we have to give low value, high value, and the size. Size is what is the size you have to give, okay? So we are giving size as we want, 50 values, okay? We want 50 values. So let's check that. Low is from 0, high is 1. We can give whatever low and high value you want, but this is uniformly distributed, okay? The values are even uniformly distributed between 10.0 and 25.3 in such a way that there is a size, or there are 50 values between that value, between 10 and 25.3. So this is size intertuple of ints, optional size. So it gives a shape, example m comma n comma n. Okay. So we have passed low, high, and size. So this is week one variable. Now let's take week two variable. So if you can see that these two are independent. Okay. I am also going to show the dependent one. Once again, we are considering the uniform distribution. So where low is equal to 10.2, comma, high is equal to 26.5, comma, size is 50, comma, 50. Okay. So we have 50 values for week one and week two. So print week one and print week two. Print week two as well. So you could see that we have week one values from 10 till 25.3. Okay. And also we have values from for week two as well. So sorry, I have given 2266. This should be 26.5. Okay. So we have values which are uniformly distributed between 10, between the ranges that is specified for week one and week two. So, so now you can see, once again read the question. The independent sample t-test or two sample t-test compares the mean of two independent groups. Okay, let's find out the mean first. So print np dot mean of week one. So week one mean comes out to be 17.8. So 17.57. Let me print week two mean as well. np dot mean of week two. So week two comes out to be, okay, once again, we are running this again and again. So that's why. So since these are randomly generated, uniformly distributed date values, so the values keeps on changing when you run it. Okay. Okay. Once again, if you run it, it keeps on changing since it's a random values that we are generating between low and high. Okay. So now you read once again. Independent sample t-test or two sample t-test compare the mean of two independent groups. So these are the independent group V1 and V2 in order to determine whether there is statistical evidence that is associated. Population means are significantly different. That is the means of week one and week two are different. That is what our hypothesis, the alternative hypothesis signifies, whereas a null hypothesis says that mean of week one is equal to mean of week two. Okay. So now let's see the standard deviation as well for these two data. np.std gives the standard deviation for week one, comma, let's print when that for week two as well. So, okay, np.week, yeah, standard deviation of week. Okay, so print np.std of standard deviation of week. So you could see the standard deviation comes out to be 4.4 and 4.7. It's almost similar. And also means are also similar. So our main motive is to find if mean is not okay. So for that, let's actually take this t-test independent, which is for two sample t-test. This also returns two values, that is t value and z value. So let's pass t and p value. Sorry, it gives t and p value. So we will pass the t-test in, and let's see the parameters that is present. So we have to pass A, that is array A, and array B, which is our week one and week two. And we have to pass anything else? No, only array week one and week two. So since this is also two-sided because as mean is not equal, so as our hypothesis, null hypothesis says, that means of uh, two independent samples are equal, okay? Mu1 equal to mu2, okay? But the alternate hypothesis says mu1 is less than or greater than mu2, okay? So let's pass here week 1, comma week 2. Now this will return pt as well as p value. So now, as I said before as well, when you are doing solving, when you are writing code in Python, it's better to go with p-value because it's a easy step and it is easy to find p-value. Even in while doing the z-test as well, we will consider p-value only instead of going with p-value. So now we will do the comparison once again. If so, let me print first, print p-value just to check what is the value it comes out to be. And then after that, if p-val is less than 0.05, the significance level is 5% by default. And if p-value is less than 0.05, print, we will reject null hypothesis. Since it's fall in the rejection region, else it's how it falls in acceptance region. So we will fail to let me write, we have failed to reject null hypothesis. Okay, so let me print this. So you could see that the p value comes out to be 0.74. Okay, and 0.74 is greater than 0.05. So we have failed to reject null hypothesis. That means our p-value for lies over here, 0.74. We have our p-value here. So I could say easily that we have failed to reject null hypothesis. Okay. So since we have seen, so once again, let me read the statement. You will understand now clearly. So independent sample t-test or two sample t-test compare the means of two independent groups. So this is where it is comparing week one and week two, and we are getting the probability value in order to determine whether there is a statistical evidence that the associated population means are significantly different. Okay. The independent sample t-test is a parametric test. Okay. Independent sample test is a parametric test. The test is also known as independent t-test. That is why we are importing t-test independent. Example is there any association between week one and week two. So this is what we are doing. Association between week one and week two is there or not? That is what we are comparing. So we have seen the dependent t-test. Now we will see we have seen the independent t-test till now. Independent sample t-test. Now let's see the paired sample t-test. So paired sample t-test, the paired sample t-test is also called dependent sample t-test. Okay, whereas this was an unpaired sample t-test. Okay, this is independent and the paired sample test is a dependent t-test. Okay, it's a univariate test that tests for a significant difference between two related variables. So it's a univariate test that says for a significant difference between two related variables. So here we are taking related variables, whereas previously we were not taking related, we were taking independent variables. Okay. An example of this is if you were to collect the blood pressure for an individual before and after some treatment, condition or time point. Okay. So according to this, if you frame null hypothesis, the what was the main idea? It's a univariate test where that tests for significant difference between two related variables. So mean difference between before and after treatment is not zero. So first, let me actually import the file first. Let's read. Let's import pandas as PD. Let's so let me say take the paired sample t-test from SciPy import. Let me take it as from scipy.stats. From scipy.stats, import t-test array. So this is t-test relational because we are taking the related data. So let me show you the data first. So data frame, let me the data frame, read CSV, read underscore CSV of the data frame. The file name is actually, this is our file, blood pressure.csv. So blood pressure.csv is our file. Okay. Let me take this file. Let me import it. So blood pressure for.csv file. Let me print the top 5 values df.head. So you could see that here here are the columns of patient with what is the sex group and age group and BP before and BP after. So this BP before is the blood pressure that was taken before a vaccination was given, and BP after was once a vaccination was given, what was the blood pressure after the vaccination was given. So this is what it is saying. So H1 is mean difference between before and after treatment is not zero. Okay. And H2, null hypothesis says that the mean difference between before and after treatment is zero. So we have to see if our null hypothesis lie is true or not. That is, we have to accept or reject our null hypothesis. So for that, let me take only BP before and BP after. So let me write a code over here. So we have our t-test relational. So this is for relational data. You could see that blood pressure before and blood pressure after is related, since we are taking the sample of the same human being. Okay. So since the sample is of the same human being, so the blood pressure will be related before and after. Okay. After the before test and after the test once vaccination is given. So let me take t-test. So even here t-test underscore relational gives two values, that is t value as well as p value. Let's pass t and p value. T comma p val is equal to t-test relation or here t-test of relation. Let's see the parameters that are present. So here we have to pass a comma b, where a and b are related to the same data. So array like the array must be of the same shape. Okay. So we have to pass, let me pass the data frame of BP before, comma. So another, so the B variable is the data frame of BP after. Okay. So now let's print P value. So P value comes out to the 0.001. So now let's say, since this is also a two-sided test, because mean difference before and after treatment is not zero, mu is less than or greater than zero, whereas mean mu is equal to zero is our null hypothesis. So if p-val, so we don't have to pass here the alternate part, so which is a two-sided here as well, two-sided tail, that is both left and right sided tail. So if p value is less than 0.05, print we fail, we reject null hypothesis, else print we fail to reject null hypothesis. Okay, so we reject null hypothesis because our p value is less than 0.05. Okay. So this is all about the t-test that we were concerned. And while doing hands-on on t-test, I would like you to solve some other problems for paid sample t-test, two sample t-test, and one sample t-test. So you can explore your options. You'll get some problems online. So now let's come to one sample z-test. So I have already taught you about z-test in the previous recordings of hypothesis testing. If you have not watched already, you can go and watch that session. So now we are using the z-test for blood pressure with some mean like 156. Okay. So now let's import pandas first. Pandas speed. And here we are importing z-test, right? So from scipy dot stats import z-test. Okay. Actually, the Z test is inside weights test. So let me correct myself first. So first you have to import. Let me. This is not so useful, I would say. So instead, importing this. Let me import from stats model. So in stats model, our Z test function is present. In stats models dot stats model dot stats wait wait stats. So inside the wait stats we have a z test function. Okay. So let me give an alias first for this stats tests as alias. So even in Z test, you will get two values, that is P value and Z value. So we are considering Z test comma P value is equal to S tests dot Z test. Okay. So as I said, inside our stats model dot stats library, we have weight stats function, and in weight stats, we have our Z test function. Okay. So we have imported our weight stats library, and inside that we have Z test function. We are importing Z test. So we are actually using the Z test function. So now let's pass x1 and value 0. Since this is a one test, one sample Z test, we are passing only one sample, and along with that, we are passing the static value. That is, value is equal to some random value. Let's say they're given, we are using Z test for blood pressure with some mean like 150. So let's use that as 156 as a static value. So value is equal to 156, and our data frame, which we have already used in our previous example, we are going to import that. We are going to use that data where we are considering the blood pressure before vaccination. Okay. So this will give us p value as well as p value. So let me print p value. So stats, stats. Okay, this is a stats model. Stats model. What's problem models? Okay, this is stat models. Okay, sorry for the mistake. So this is stats model. Stats models dot stats, from stats models dot stats import weight stats, and in that weight stats we have a z test function. Okay, we have given an alias for weight stats as s test. So now we can also print z test on z test. So z test value comes out to be 0.43. Okay, so now let's take p value. If p val is less than 0.05, print reject null hypothesis. Okay, else, sorry, print reject null hypothesis. Else print fail to reject null hypothesis. So you can see that our p value is, let me, uh, so the p value is greater than 0.665, so point is greater than 0.05. So we are failing to reject null hypothesis. Okay? So we have to accept, we have to accept the null hypothesis, but let me check it once again. Let me change this value to 159 itself. Okay, we are rejecting null hypothesis. Let it be 156 itself. Okay. So you could see how we can perform hypothesis testing using the function z-test. Okay, we have seen that. So similarly, we have seen here, we have passed one static value and we have passed one sample. Okay, so one sample we have passed, which is from our data frame, and we have compared that with our static value. Now let's do the two samples z test. Okay, in two samples z test is similar to t test. Here we are checking two independent data groups and deciding whether sample mean of two groups or equal or not. So H naught is mean of two group is equal 0, and H1 is mean of two group is not 0. Actually, this is the two group is equal or not. That is what we are testing. So let me check it first. So so here we are considering two independent data groups and deciding whether sample mean of two group is equal or not. So let's take the dependent group itself for this example. Yeah, let's see. We are checking in blood data and blood and before day blood data. We're checking the data after blood and before blood. That is checking blood data where blood pressure is calculated before and after vaccination. Okay. So now let's do the Z test here as a Z test comma P value is equal to S tests. So this test, right? S test is the variable name dot Z test of. So let me pass here. Now instead of passing a static value, we are passing two values, x1 and x2. So x1 and x2 are independent variables, but let me take instead dependent. Let me take it from the same data frame, that is blood pressure BP before, comma, data frame of BP after. Okay. And this will give us the p value, p value. If p val is less than 0.05, print. Let me copy this code. Okay, let me run this. So you could see that our p value is less than 0.05. So we are rejecting null hypothesis. Okay. So this should be mean of two groups is equal and mean of two groups is not equal. Okay. Okay, we have modified it. And actually, the thing is that we are taking a dependent data since we are taking it from the same data frame. So these are dependent, right? It's fine, okay? You can once again take that week one and week two and just use that formula and just check what kind of answer you get. So we have completed our Z test for now. So you can go now and perform some. You can do some problems related to Z test. Will get online. You can read it out. The document you can read. You can pause your video and read it. So now let's do the one-way ANOVA. So I had already discussed about analysis of variance. That is what ANOVA is, analysis of variance. That is V1 and V2. So let's do the ANOVA part. So three different categories of plant and their weight and need to check whether all three groups are similar or not. So three different categories. Let me show you the data first. Let me read the CSV file. Okay, this is the CSV file, and in this data we have weight column and a group column, and in the problem statement we have three different category of plant. Okay, the three different category of plant are CTRL, TR1, and TR2, and the weight and their weight are given. Okay, and their weight, so their weight is also given, and need to check whether all three groups are similar or not. Okay, so we in ANOVA we have to check if all three groups, whatever is given here, CTRL, TR1, and TR2, we have to check all three groups weight and their weight is similar or not. Okay, all three. So let me first import pandas library, but we have already did that, right? Maybe we'll do it again. Import pandas as PD. You don't have to do again and again import, but you can. We have done it already previously. I'm just doing it for your reference. So let me take AF ANOVA is equal to PD dot read CSV read CSV, and inside that, let's pass our planned growth.csv. Let me print it, df ANOVA. What happened? What happened? Let me check it. Board has no attribute read CSV. Sorry, this is CSV. Okay. So you could see in the group, we have CTRL, TR1, and TR2 are the group, and we have to, these are the three different categories. So let me say what is one-way ANOVA. I had already explained in the previous video, but one way is we are comparing two or so we are if the comparison of two or more groups based on one factor, then it is one-way ANOVA. Okay. Um, so based on one factor, we are actually doing the comparison of these three groups. So for comparison of these three groups, let me write the code for that. So the data. So, so what we are taking here. So we want these three values, right? CTRL, TR1, and TR2. Okay. So GRP or GRP in group. Okay. GRP is what? DF ANOVA of for GRP in group, DF ANOVA of what you want. Actually, we have to pass weight. We want weight, right? GF, right? And we want to pass weight, but we have to take only those group where the weight is subsequent to its group part. Okay, so we want this. For CTRL, what is the weight values, and for TRT1, what is the weight values, and TR2, what is the weight values. We'll form a dictionary. So for group in groups, so we get CTRL1, CTR1, and TR2 over here. So we're taking ANOVA of weight where DF underscore ANOVA of group. So we have to pass it in for is equal to GR. Hope this is correct. Let me check it. Let me run this code. Okay, so what's the problem? Name group is not defined. So this is group, right? EFNO of group. So this should be actually we are not accessing the column. It's accessing column, right? So dfnoma dot group. CRO UK8. Let me column. Name group is not defined. What is this? Okay, let me check. GRO. Actually, sorry, this is data frame of that is the value data frame. So you have to use pandas. So let me create a group variable over here. UPS UP is equal to PD dot unique of data frame ANOVA dot group dot values. So now let me pass 0 UPS groups. Yes. So now what I did here is that whatever value we had, right? So what I did here was, let me see. Yeah. First, actually, I took all the unique values that are present in our ANOVA data frame, where only we use the group values. Okay, so we are did the group by function where we wanted only the values which are unique in the group column. Okay, so we have actually stored that unique values in our groups variable. You can see here, if you print groups, you will get unique values, that is CTRL, TR1, TR2, that are present in the group variable group column. So we used pd.unique function to extract the unique values from our data. Now that I have passed those unique values in our group for group in groups, I have accessed each value, and for each value, I have actually passed the weights, whatever weights that are present, where ANOVA.group is equal to this. Okay, wherever ANOVA.group this is equal to this value, then we are actually accessing that element, and then we are actually finding out the weight. So you could see that from here to here, you will get CTRL 5.14, 4.17 till 5.14 values get printed for CTRL. Similarly, for TR1 we will get values printed, and TR2 will get values printed from 6.31 to 5.26, 6.31 to 5.26. Okay. So now let's complete this. So now we will write. um, so this is ANOVA, right? So we have to import function. So let me import f1 right? So from import stats, scipy.stats, import from stats from scipy, from scipy import stats. Okay, so I have imported stat from scipy. Okay, so there is an error from SciPy. So from scientific Python library, we have imported stats. So now we have to in stats, we have one way ANOVA. So here also we'll get two values, that is F test. So here we'll get F test. So usually do F test for ANOVA. So we'll get F test as well as P value. So stats dot F one way. F one way. So this is for one way ANOVA. So pass the data over here. So D data of. So what was the question? Three different category of plants and their weight need to check whether all three are similar or not. So now we are considering the three categories of data. That is, which are the three categories? We have to pass CTRL1, CTRL, comma, D data of TRT1, comma, D data of TRT2. Okay. So we are doing the hypothesis testing where we are considering three categories are actually compared based on one factor. So here we are comparing based on weight. Okay. So let's print p value. If p value is less than 0.05, print. Let me just copy the code over here. Print. Okay, so let me run this code. So you could see that our p-value comes out to be 0.015, which lies in the rejection region. Hence, we are rejecting null hypothesis. Okay? We have rejected the null hypothesis since our p-value is 0.01 and it should have been less than 0.05. So we could say that from this statement, we can say that the three different categories of plants that we have considered, their weights are different. Okay. And when the comparison was done, it can be seen that their mean weight is different from whatever was calculated from this value, whatever was expected. So we have to reject null hypothesis because so there is no equality. So the mean is not equal. Mean of CTRL is not equal to mean of data one, data of TRT1 or mean now is not equal to either. Like we can say that for one way ANOVA, this three factors what we have considered, even if one of the category is not matching, right? I mean, if even if mean of this and this equal, and if it is not equal to this, then also it will be reject null hypothesis. Okay, it all should be similar. Okay, then only this statement will hold true that accept null hypothesis. Otherwise, if one of them is not matching with whatever was expected, that is, even if one of the uh, mean is different from other two, then also we will have to reject the null hypothesis. So here is an example of on a shell measurement in the muzzle Mytilus rostrum from 5 location. These are the locations that are given, that is Tillamook, Newport, Pittsburgh, Magadan, Tivermini. Okay, so we are using F1 way. This is also an example of one-way ANOVA. So previously also we have considered one-way ANOVA where we had actually find out F-test value as well, but we don't have to worry about that because we don't have, then we, if we have F-test, then we also have to see the F-tabular and we have to compare with that. So we are here also we are taking the p-value. So in this example, so we are performing one-way ANOVA testing for this as well. So let me take the f comma p value is equal to f one way. So we are importing f1 way ANOVA for this example. So let me take all these variables. Import so here also while performing the one-way ANOVA, even if one of the variables that we have considered, if one of the arrays that we have considered, the mean value is different from other four, then also we have to reject null hypothesis because here also we are considering that all are equal or similar, or that is mean values they are having. But even if one of them fails to hold that, we are actually a null hypothesis. So let's print p-value and check what is the value. So you could see that p-value comes out to be too small. So hence we can say once again that we have to reject our null hypothesis because one or the other with one or more multiple variables are not having the similar characteristics. Okay. So because of that, I mean, if one or more groups are not having the similar characteristics, it can be here the whatever values we have considered over here. So now let's come to two-way ANOVA. So in two-way ANOVA, so this is used when you have two independent variable and two groups. Okay. So as I said earlier in the last video, that two-way ANOVA when comparing two or more groups based on two factors, that is called one or two-way ANOVA. So here we have our data frame. Let me print it. So this is the data frame that we have the blood pressure before and blood pressure after. So let me run this code first. Now let me run this data frame. Yeah, you can see that we have three columns: water, sun, and height. So now we are performing. Actually, let me take the only head part here. Okay, so we have three. We have to run whole data frame. So you see that we have created a dictionary of values where for water column we have daily and weekly. 15 times it is repeated. So daily is repeated 15 times and weekly is repeated 15 times. Then we had sun and we have repetition as low, mid, high, 5 times each. So low 5, mid 5, high 5. For weekly it is low 5, mid 5, high 5. So similarly it is repeated twice, sun. And height we have given some height values 6, 6, 5 random values we have given. So now, so what you have to do, first let me import stats model dot the API as SM. So for this problem, we are going to use linear regression. I'm going to teach you about the linear regression in the later section of the classes when I'm going to do the machine learning. So we are using linear model over here. So from stats model, see stats models, okay? From stats model dot formula dot API import OLS. OLS is an ordinary least square. It's a linear regression model. So now let's perform two-way ANOVA. Okay. So we know that height of the plant depends on either sun or water or the combination of water and sun. So how we will write that in the code? So let me write model is equal to ordinary least square of height is dependent on sun. That is how we write tilde height tilde. It's dependent on C of sun. This is C, right? C of sun, C of water. It's dependent of water or sun. Or it's a combination of sun and water. C is column, okay? C is column sun, column water. Or it's a combination of column water and sun. And what is the data we have? Data is DF, data frame. So we have to train our model using fit. Now let's do sm.stats.ANOVA underscore linear model of model comma type 2. So what happened here? I tilde from stats models dot API, stats models dot API, import model stats stats model dot API. Okay. Okay, what we get? So these are the values we got. So you can see the probability of only water is 0.00527, which is less than zero point 0.5. So you can see which is less than 0.05 and C of sun is also less than 0.05 and the combination of water and sun has a greater value. So here you can see, we can see the following p-values for each of the factors in the table. Water p-value is 0.000527, sun p-value is this much, and water and sun combination p-value is 0.12. Since the p-values for water and sun are both less than 0.05, this means the both factor have statistically significant effect on plant. Okay, they have both have the statistically significant effect on plant height, and since the p-value for interaction effect, this is the both water and sun is not less than 0.05. This tells us that there is no significant interaction between sunlight exposure and watering frequency. Okay, this is all we have learned. I want you to try this too. So write down the decision loop for each condition provided for the two-way ANOVA here. Okay, so write the decision loop for each way, like take this and probability and take this and compare it with the 0.05 probability and write the conclusion like this means that both factors are significantly affect on plant health, like that kind of thing. That is, you have to reject or fail to reject null hypothesis. You have to consider based on the factors. So that is null hypothesis, no significant effect on plant health is a null hypothesis, and alternate hypothesis is significant effect on plant health hypothesis. This is the condition, if condition you have to write, format for these values, and also try to write null and open alternate hypothesis for all the examples that we have discussed so far, and also apply the paired sample z test to the paired sample t test example. Okay, so whatever we had done with p value, try to do it with the paired sample z test to the paired sample t test example. So whatever paired sample t-test you had done, do the same for the paired sample t-test. Okay. This is all about the hypothesis testing hands-on I wanted to discuss. Thank you for attending this session. I will be discussing more related to the statistics that is required for data science in the coming lectures.